The paper delves into the solution of regular singular Volterra equations on complex domains, leveraging the inverse Laplace transform to convert a linear differential equation on a complex domain into a simpler Volterra integral equation on a real domain. This transformation reveals hidden structure and facilitates analysis. The main result of the paper is the existence of a unique solution for a certain kind of regular singular Volterra equation on a complex domain. This is demonstrated through a motivating example involving level 1 differential equations and the use of Laplace transform methods. Function spaces for holomorphic Volterra operators are detailed, including weighted holomorphic L infinity spaces and continuous inclusions between different HL infinity spaces. The solving of holomorphic Volterra equations is also covered, encompassing the construction and regularity of the prototype solution, showing that the operator V makes the prototype solution less singular, and demonstrating the existence and uniqueness of a fixed point. This research provides significant insights into the structure and solvability of these complex equations, offering a novel approach to tackle them and paving the way for further investigations in this area. The Laplace transform enables the conversion of exponential-type functions of a real position variable into holomorphic functions of a complex frequency variable, facilitating the application of Volterra equations' favorable properties to linear differential equations. This transformation allows for the analysis of certain differential equations with irregular singularities in the frequency domain, which can be pulled back to Volterra equations with regular singularities in the position domain. The authors focus on level 1 equations, a specific subclass of differential equations that include classical examples such as the modified Bessel equation and the Airy equation. These equations exhibit special solutions when the integration base point coincides with a regular singularity, featuring an O(1) zeta singularity at zeta equals 0 and being of exponential type. The paper aims to justify the existence and uniqueness of these special solutions using a Banach space of holomorphic functions. This is achieved by establishing an existence and uniqueness result, which provides a rigorous mathematical framework for understanding the behavior of solutions that may appear unrelated in the frequency domain but are linked by analytic continuation. The importance of this research lies in its ability to provide new insights into the properties of linear differential equations with singularities, enabling the development of novel solution methods and techniques. By exploring the connections between the frequency and position domains, this study contributes to a deeper understanding of the underlying mathematical structures that govern these equations. In the complex plane C, consider a simply connected open set omega that touches but doesn't contain the origin, satisfying the star property. Let phi be a complex-valued function and omega a non-negative, real-valued function, both defined on omega. We can express the modulus of phi, denoted as phi, as bounded by a constant multiple of omega, written as phi omega. We focus on the prototype operator V0, a holomorphic Volterra operator characterized by a separable kernel and a regular singularity at the origin. This operator transforms each holomorphic function phi on omega into a new holomorphic function, V0 phi a, through integration with respect to the kernel K0, a. The operator V0 is defined as an integral operator, where V0 phi a equals integral omega K0 a z phi z dz, with K0 a z being the kernel function. The kernel K0 a z is separable, meaning it can be written as a product of functions of and z, respectively. The regular singularity at the origin implies that the kernel K0 a z has a finite limit as z approaches the origin. This property is crucial in our analysis, as it enables us to establish boundedness properties of the operator V0. Throughout this paper, we explore the properties and applications of the operator V0, leveraging its holomorphicity and the star property of omega to derive novel results and insights. The kernel K0, a crucial component in the analysis of the operator V0, is assumed to be separable, meaning it can be factored into a product of two functions, one depending on a and the other on a. This factorization is given by K0 a equals q a p a, where p and q are holomorphic functions on omega. The kernel K0 also has a regular singularity at zeta equals 0, which implies that the difference between K0, a, and a certain constant times zeta, a, is bounded in a neighborhood of zeta, a, equals 0 in omega. Furthermore, the bound K0, a, less than sigma, zeta, a, holds for some sigma greater than 0 when zeta, a, is close to 0 in omega squared. Additionally, the condition diag0 lambda increment is introduced, requiring that K0, a, is bounded by a constant times zeta, a, lambda increment zeta, a, for all a in omega. This condition explains the shape of omega, as it must avoid the zeros of p while stretching out towards infinity. An optional condition on p, denoted as regp, b, is also mentioned, stating that p can be expressed as b zeta plus o, zeta, 1 plus o, at zeta equals 0 for some non-zero constant b and o greater than 0. The paper then moves on to discuss the perturbed operator v equals v0 plus v star operator. The perturbation v star operator does not have a separable kernel, but it has a smoothing effect that counteracts the singularity of v0. In this section, the authors introduce a kernel function k star operator associated with a holomorphic Volterra operator v star operator, which must vanish to some order gamma greater than 0 on the diagonal in omega 2. This requirement, along with two others, is made precise in condition diag star operator, gamma, lambda increment. The kernel k star operator is a holomorphic function on omega 2, allowed to have a simple pole at zeta, a, equals 0, but not sharper singularities. The authors also impose an exponential bound on the growth of k star operator away from the diagonal, similar to condition diag 0, lambda increment, on K0. The authors then present their main results. They show that when V is a regular singular Volterra operator, the equation F equals Vf has a unique solution of a certain form. For the prototypical operator V0, this solution can be written explicitly as F0, A, equals 1, P, A, express, minus sign integral of BQPD zeta, where P and Q are functions defined in section 1.3.2. This result is stated in Theorem 1 and will be proven in section 3.2.1. The solution F0 has, at worst, a mild power law singularity at zeta equals 0. With stronger constraints on V0, the authors can also ensure that F0 grows at most exponentially as zeta, right pointing arrow infinity. The function spaces defined in section 2 express both of these regularity properties. Specifically, Theorem 2 states that if V0 satisfies condition sin tau, then on a small enough neighborhood of zeta equals 0, F0, zeta, tau minus 1, and if V0 also satisfies condition diag 0, lambda increment, then F0 belongs to the space HL infinity tau minus 1, omega, defined in section 2. The proof of this result is given in section 3.2.2. Theorem 3 and its associated lemma 1 address the solution of a specific equation, F equals Vf, where V is an operator composed of V0 and V star operator. The conditions on V0 and V star operator ensure the equation has a unique solution in the affine subspace F0 plus HL infinity tau minus 1 plus gamma, omega. This solution is based on the prototype solution F0, which belongs to the same space. The uniqueness remains true for any rho greater than tau. The proof of lemma 1 utilizes the contraction mapping theorem in sections 3.4.3.5. Proposition 10 identifies relevant subspaces where V acts as a contraction, reducing theorem 3 to lemma 1 in section 3.5. Proposition 9 ensures the regularity of the inhomogeneous term V star operator F0, as described in Theorem 2. When V0 satisfies condition regp, B, O, Theorem 3 provides a unique solution in the affine subspace ZT-1 plus HL infinity rho minus 1, omega, for rho greater than tau. This result is a significant advancement in understanding the properties of the solutions to the given equation, particularly concerning their uniqueness and the impact of various conditions on the operators V0 and V star operator. The authors acknowledge the contributions of Ki-Hyun Kim, Agelaki Menegaki, and Sungjin Oh to the early stages of this work, which is funded by the European Research Council under the Horizon 2020 Research and Innovation Programme. This paper delves into the concept of function spaces for holomorphic Volterra operators, focusing on weighted holomorphic L-infinity spaces. Let omega be a simply connected open set in the complex plane that touches but does not contain the origin. The space of continuous complex-valued functions on omega, denoted by C, omega, is equipped with the compact open topology. The subspace of holomorphic functions, H, omega, is a closed subspace of C, omega. Fixing a real constant lambda, the authors consider holomorphic functions on omega that are bounded by constant multiples of E lambda, zeta. These functions are said to be uniformly of exponential type lambda. The space of such functions, denoted by HL infinity 0, lambda, omega, is equipped with the norm parallel F parallel 0. Lambda equals sup omega E minus lambda, zeta, F. The inclusion map from HL infinity 0, lambda, omega, to H, omega, is continuous, and it is shown that HL infinity 0, lambda, omega, is a complete space. The proof of completeness involves showing that a Cauchy sequence in HL infinity 0, lambda, omega, converges to a function f in H, omega, and that the sequence converges to f in the norm parallel 0, lambda. This is achieved by using the fact that the inclusion map is bounded with respect to each of the seminorms on H, omega, given by f, rightwards arrow from bar supike, f, for compact subsets K subset of omega. In the realm of complex analysis, the space HL infinity sigma, lambda, omega, is defined as a collection of holomorphic functions bounded by constant multiples of zeta, sigma E lambda, zeta. The norm in this space is given by the supremum of zeta minus sigma E minus lambda, zeta, f, over omega. This space is complete and exhibits continuous inclusions with other HL infinity sigma, lambda, omega, spaces, showcasing intricate relationships between them. A related space, HL infinity 0, omega, consists of functions of exponential type and has a specific topology. The continuous inclusions between HL infinity sigma, omega, spaces are also well defined, with distinct properties for each space. These spaces and their properties are crucial in understanding the behavior of certain classes of functions in complex analysis. The authors construct the prototype solution F0 from the kernel of V0, a separable operator that gives V equals V0 plus V star operator its regular singularity. They show that F0 satisfies the equation F0 equals V0 F0 and belongs to the space HL infinity tau minus 1, lambda 0, omega. The perturbation V star operator has a smoothing effect on F0, reducing the sharpness of any power law singularity at zeta equals 0. This sends F0 into HL infinity tau minus 1 plus gamma, omega, a space with smoother functions. The authors demonstrate that V sends F0 into the affine subspace F0 plus HL infinity tau minus 1 plus gamma, omega, suggesting a solution within this subspace. They prove V is a contraction of HL infinity tau minus 1 plus gamma, lambda, omega, when lambda is large enough, ensuring a unique fixed point in F0 plus HL infinity tau minus 1 plus gamma, omega. The proof of theorems 1 and 2 involves the construction of the prototype solution F0, achieved by rewriting F0 as 1, p, chi. This construction is crucial for the analysis of the regular singular Volterra equation and its solution. The calculation of V0 F0 is greatly simplified by observing that d chi equals minus q over p times chi d zeta. This leads to the expression for V0 F0 of a, which is equal to 1 over p of a times the integral from 0 to a of d chi, further simplified to F0 of a minus 1 over p of a times the limit as zeta approaches 0 of chi. To prove that V0 F0 equals F0, it is necessary to show that the limit as zeta approaches 0 of chi equals 0. This is achieved by using condition sin tau, which provides a radius delta greater than 0 and a constant c such that the absolute value of p minus tau times zeta is less than c whenever the absolute value of zeta is less than delta. The bound provided by condition sin tau is used to rewrite the integral in the definition of chi, resulting in an expression for chi of a in terms of zeta of a, zeta of b, tau, and an exponential term. By choosing a base point b in omega such that the absolute value of zeta of b equals delta over 2, the exponential factor can be bounded between two constants whenever the absolute value of zeta of a is less than delta. Since tau is positive, this is sufficient to show that the limit as zeta approaches 0 of chi equals 0, implying that v0 f0 equals f0. The regularity of the solution is addressed in Theorem 2, which consists of two results with different conditions. Proposition 6 states that if v0 satisfies condition sin tau, then, on a small enough neighborhood of zeta equals 0, the absolute value of f0 is less than or similar to the absolute value of zeta raised to the power of tau minus 1. This result provides a key insight into the behavior of f0 near zeta equals 0. The proof of Theorem 1 is re-examined to establish a stronger conclusion concerning the relationship between chi and zeta on the region zeta less than delta. This enhanced conclusion subsequently demonstrates that f0 less or similar zeta tau minus 1 e lambda 0 zeta over the region zeta less than delta for some real constant lambda 0. The proof also establishes that k0 a less or similar 1 zeta a e lambda increment zeta a minus zeta a leading to a bound on q p is less than or equal to c increment along the diagonal in omega 2. This bound is pivotal for showing that f0 belongs to the space HL infinity tau minus 1 omega. The function f0's properties, particularly its behavior around the origin, are discussed. It begins by bounding the function using the region zeta is greater than or equal to delta and another arbitrary point b. This leads to an expression for f0 a that involves the exponential of an integral. By setting lambda 0 equal to the sum of lambda increment and c increment, the expression simplifies, showing that f0 is bounded by zeta tau minus 1 times an exponential term over the region zeta is greater than or equal to delta. This, combined with the earlier argument for the region zeta less than delta, yields the desired result. Proposition 8 states that under certain conditions, f0 can be expressed as mzt minus 1 plus o zeta tau minus 1 plus o at zeta equals 0. The proof involves showing that f0 a can be written as a series involving the exponential of an integral, which converges to the desired form at the origin. The exponential factor's properties are examined in relation to the zeta factor, with a focus on their behavior near the critical point zeta equals 0. A key contribution is the establishment of the convergence of an improper integral, which enables the derivation of an explicit expression for the exponential factor. This result, in turn, is used to demonstrate that the prototype solution f0 belongs to the function space HL infinity tau minus 1 omega. Notably, the smoothing effect of the operator v star operator is highlighted, which maps functions from HL infinity sigma lambda omega to HL infinity sigma plus gamma lambda omega under specific conditions. This mapping property is crucial, as it implies that v star operator can increase the regularity of functions by gamma orders, thereby providing a means to control the smoothness of solutions. Proposition 9 establishes that the function v(f) is uniformly bounded in the domain omega under certain conditions. Specifically, the proposition assumes gamma greater than 0 and sigma greater than 1, ensuring the well-definedness of the gamma functions involved. The proof also relies on the condition diag gamma lambda delta, which is crucial for the boundedness of v(f). The corollary to proposition 9 examines the prototype solution f_0 from equation 1 and its relationship with the function v(f_0). Notably, if v satisfies the condition diag gamma lambda delta, then v caret f underscore 0 belongs to the space HL caret infty underscore tau 1 plus gamma c dot omega. This result is derived by applying theorem 2, which states that f underscore 0 belongs to HL caret infty underscore tau 1 c dot omega, and then using proposition 9 to conclude the desired result. The significance of this finding lies in the establishment of a bounded v caret f in omega, which has important implications for subsequent analyses. The conditions imposed on gamma and sigma ensure that the gamma functions involved are well defined, while the condition diag, gamma, lambda, delta provides the necessary constraint for boundedness. In this section, the authors seek to establish proposition 10, which asserts that V is a contraction of HL infinity rho minus 1 lambda omega under certain conditions. Specifically, they require V0 to satisfy conditions sing tau and diag 0 lambda increment, and V star operator to meet condition diag star operator gamma lambda increment. To achieve this, they first select some sigma element of tau rho and employ proposition 11 to identify a neighborhood omega near of zeta equals 0 where k a is less than or equal to sigma zeta a for all a element of omega near. The authors then partition omega into omega near and omega far based on the value of zeta. They proceed to bound zeta minus rho minus 1 e minus lambda zeta v phi by sigma rho barred bl phi barred bl rho minus 1 lambda on omega near in section 3.4.4, and by an arbitrarily small constant multiple of barred bl phi barred bl rho minus 1 lambda on omega far in section 3.4.5. This results in barred bl v phi barred bl rho minus 1 lambda is less than or equal to sigma rho barred bl phi barred bl rho minus 1 lambda when lambda is large enough, thus proving proposition 10 since sigma less than rho. Proposition 11 is also presented, stating that for any sigma greater than tau, one can ensure that k a is less than or equal to sigma zeta a by keeping a and a sufficiently close to zeta equals 0. This is achieved by choosing some sigma 0 element of tau sigma and making delta greater than 0 small enough to satisfy the condition k0 a is less than or equal to sigma 0 zeta a. This section demonstrates the author's approach to establishing the contraction property of V, which is crucial for their overall argument. By carefully dividing the domain into different regions and applying various bounds, they are able to show that V shrinks less singular functions, contributing to the main result of the paper. The kernel function k a exhibits distinct properties when one of its arguments is kept away from a specific point zeta equals 0. A decomposition of the kernel function into two parts, k0 a and k star operator a enables bounding by a term dependent on the difference between zeta a and zeta a. This bound holds for all a in the subset omega, where zeta a less than delta and zeta a less than delta, provided both k0 and k star operator satisfy specific diagonal dominance conditions. Furthermore, an alternative bound for the kernel function is established when the first argument a is kept away from zeta equals 0. By selecting a subset omega far of omega that does not intersect with zeta equals 0, the kernel function can be bounded by an exponential function of zeta a with a coefficient dependent on the choice of lambda greater than lambda increment. This result applies to all a in omega far and a in omega. These bounds have significant implications for understanding the behavior of the kernel function under specific conditions, particularly when one of the arguments is distant from zeta equals 0. In this section, the authors initiate their calculation by introducing an inequality for each a in omega, which is fundamental for their subsequent analysis. The inequality involves the norm on HL infinity rho minus 1 lambda omega and the kernel k a of the integral operator V. The approach is divided into two parts based on whether a is in omega near or omega far. For in omega near, a straight integration path within the sector of a disk leads to an upper bound on zeta a minus rho minus 1 e minus lambda zeta a v phi a in terms of sigma and the norm of phi. This result is crucial for proving proposition 10. For in omega far, proposition 12 from section 3.4.2 is employed to find a constant m such that k a is less than or equal to mu lambda zeta a minus zeta, where lambda greater than lambda increment. This bound is essential for demonstrating the contraction property of V in the following sections. The authors continue their analysis of the contraction properties of the operator V, aiming to show that V is a contraction in the space HL infinity rho minus 1, lambda, omega. They start by bounding zeta a minus rho minus 1 e minus lambda zeta a v phi a using previously established bounds on K and the properties of the measure mu. This bound is uniform over all element of omega far, allowing it to be made arbitrarily small by increasing lambda. To refine this bound, the authors split the integration path into two parts, using worst-case estimates for the exponential factor at the beginning and for t rho minus 1 at the end. By combining these bounds, they demonstrate that zeta a minus rho minus 1 e minus lambda zeta a v phi a can be made arbitrarily small over all element of omega far. This completes the proof of proposition 10, establishing that V is a contraction in HL infinity rho minus 1, lambda, omega. The authors then prove lemma 1 and theorem 3 by choosing a large enough lambda to ensure V is a contraction and G belongs to HL infinity rho minus 1, lambda, omega. This is possible due to proposition 10, which guarantees the existence of such a lambda. The paper establishes the uniqueness of the fixed point in the space HL infinity rho minus 1, omega, for the map F, maps to right pointing arrow VF plus GIS. It begins by demonstrating the existence of a unique fixed point in HL infinity rho minus 1, lambda, omega, ensured by the assumptions about van der Rohe and the definition of HL infinity rho minus 1, lambda, omega. The uniqueness is then extended to HL infinity rho minus 1, omega, by showing that any fixed point in HL infinity rho minus 1, lambda, omega, maps to the unique fixed point in HL infinity rho minus 1, lambda, omega, under the inclusion for all lambda, is less than or equal to lambda. The proof relies on the contraction mapping theorem and the uniqueness of the solution to an inhomogeneous equation, confirming the uniqueness of the fixed point in HL infinity rho minus 1, omega. Proposition 13 assumes that V satisfies condition REGP, B, O, and demonstrates the existence of a unique solution to the equation F equals VF within the affine subspace ZT-1 plus HL infinity rho minus 1, omega, under specific conditions. This result is achieved by leveraging propositions 7 and 8, which establish a connection between the solution space and a constant m, and theorem 3, which ensures the uniqueness of the solution. The proposition's conditions are further clarified, emphasizing the importance of ρ being within a specific interval. A motivating example is then presented, focusing on level 1 differential equations. Understanding regular singular Volterra equations can aid in studying these differential equations, particularly in the context of analytic solutions in the frequency domain. The example outlines the construction of solutions through regular singular Volterra equations in the position domain, ensuring the existence, uniqueness, and well-defined Laplace transforms of these solutions. The application of Laplace transform methods to solve level 1 differential equations, specifically those in the form p phi equals 0, is a key focus in this section of the research paper. These equations are classified as having regular singularities at zeta equals 0. To address these, the authors introduce a new notation, OA, which denotes a domain that touches but does not contain zeta equals alpha. They also redefine the function space HL infinity sigma lambda OA as a space of holomorphic functions on OA with power law singularities at zeta equals alpha and uniform exponential type lambda. In addition, the authors adapt conditions for Volterra operators, such as V alpha 0 and V alpha star operator, to describe regular singularities at zeta equals alpha. These conditions include boundedness and exponential decay of the kernel functions k alpha 0 and k alpha star operator in terms of zeta a alpha and zeta a respectively. The paper emphasizes that these adaptations will be further explored in an upcoming paper using Laplace transform methods. This section provides a detailed analysis of the application of Laplace transform methods to solve level 1 differential equations with regular singularities. By introducing the notation OA and redefining the function space HL infinity sigma, lambda, OA, the authors offer a novel approach to addressing these complex equations. The adaptation of Volterra operator conditions adds depth to this analysis, providing researchers with a comprehensive framework for understanding and solving these types of differential equations. The authors delve into the Laplace transform, a pivotal concept in complex analysis, and its properties within the context of fractional integration. The Laplace transform, denoted as L-Thales, alpha, is a mapping from functions in HL infinity sigma, lambda, OA, with sigma greater than 1 and lambda element of R to holomorphic functions on the half-plane Re, z theta, greater than lambda in the frequency domain. It is defined by the formula L-Thales, F equals integral G's, alpha Ez zeta phi d zeta, where G's, alpha is the ray that leaves zeta equals alpha at angle theta. The focus then shifts to the action of the Laplace transform on integral operators, specifically the fractional integral partial differential ends, alpha, which is a Volterra operator defined by partial differential ends, f a equals 1, gamma, nu, integral a zeta equals alpha, zeta, a, zeta, nu 1 phi d zeta. This operator satisfies the semigroup law micro zeta, alpha partial differential ends, alpha equals micro ends, alpha for micro, nu element of 0, infinity, and agrees with ordinary repeated integration when nu is an integer. The authors prove proposition 14, stating that for each nu element of 0, infinity, the fractional integral partial differential ends, alpha maps HL infinity sigma, lambda, OA, right pointing arrow HL infinity sigma plus nu, lambda, OA, continuously for all sigma greater than 1 and lambda is greater than or equal to 0. The proof involves rewriting the fractional integral as a Volterra operator with a specific kernel, allowing the authors to establish the continuity of the mapping. This section provides a detailed analysis of the Laplace transform and its connection to fractional integration, highlighting the smoothing effect of fractional integration on power law singularities at zeta equals alpha. The Laplace transform of the fractional integral of a function satisfies a specific condition, enabling the mapping of functions between different spaces. This property is leveraged to define a Volterra operator in the position domain through the Laplace transform of a function. The transform's direction and the function's domain are crucial for ensuring the transform's well-definition. The conversion of differential operators into Volterra operators is demonstrated through a lemma, highlighting the significance of the Laplace transform in this context. The primary outcome of this section is the establishment and proof of a fundamental theorem, focusing on the Volterra equation Pf equals 0. A simply connected open set omega alpha is chosen, which intersects zeta equals alpha and does not intersect any other roots of p minus zeta. By lemma 2, the Laplace transform of the solution to this equation satisfies p phi equals 0. Theorem 4 is presented, considering a root minus alpha of p where ta equals q minus alpha, p minus alpha, is real and positive. This theorem guarantees the existence of a unique solution SA in the affine subspace zeta minus 1 plus HL infinity ta, OA, of the space HL infinity ta minus 1, OA, for the equation p apsa equals 0. The proof of theorem 4 commences by rewriting the equation p af equals 0 in the form phi equals v af, where v alpha is a Volterra operator as described in section 1.3 under the reinterpretation from section 4.3. The equation is then expanded, and by isolating p phi on the left and dividing both sides by p, an equivalent equation is derived. This equivalent equation is then written in the form phi equals V alpha, where V alpha equals V alpha 0 plus V alpha star operator, and the kernels of V alpha 0 and V alpha star operator are defined. The kernel of V alpha is shown to extend meromorphically over all of C2, and the convergence of the power series defining Kr is confirmed. This result holds significant implications, as it ensures the existence of a unique solution to the Volterra equation P apsa equals 0 under specific conditions on the root minus alpha of P and the set omega alpha. The proof relies on the application of proposition 13 and the properties of Volterra operators, as well as the careful manipulation of the equation P af equals 0 into a suitable form. The function R, Z, is defined as the ratio of two polynomials, Q, Z, and P, Z, with a specific condition on their roots. A kernel, V alpha 0, is introduced with a separable form. The primary objective is to demonstrate that V alpha 0 satisfies the singularity condition, as stated in section 1.3. To achieve this, the authors first prove that R, Z, is well defined throughout C2 by showing that its series representation converges for Z greater than A, where A is a constant. Then, using a partial fraction decomposition of 1, P, zeta, they derive an expression for Q, zeta, P, zeta, in terms of the roots of P, Z, and the polynomial Q alpha, zeta. The key result is that Q, zeta, P, zeta, ta, za, is bounded on a neighborhood of zeta equals alpha in OA, where ta equals Q, alpha, P, alpha. This is achieved by expressing the right-hand side as a sum of terms involving Q, zeta, Q alpha, zeta, and P, beta, for each root beta of P, Z, excluding alpha. Since Q and Q alpha are polynomials, the right-hand side is bounded on any neighborhood of zeta equals alpha that avoids the other roots of P, Z, and infinity. This analysis supports the claim that V alpha 0 satisfies the singularity condition, as required by proposition 13. Consequently, the validity of the kernel V alpha 0 and its application in the research context are established. For any sigma greater than ta, the bound zeta A alpha Q zeta A P zeta A is less than or equal to sigma holds when A and A are close enough to zeta equals alpha. This is demonstrated by taking the absolute value of both sides of the given equation, 8, under the assumption that ta is real and positive. By bringing zeta A closer to alpha, the middle term can be made as small as desired, and similarly, by bringing zeta A closer to alpha, the sum can be made as small as desired. This implies that for any sigma greater than ta, the bound zeta A alpha Q zeta A P zeta A is less than or equal to sigma holds over some neighborhood of zeta A equals alpha alpha in omega squared alpha. The authors then address the condition diag 0 lambda increment on V alpha 0, which is satisfied. To bound zeta A alpha K alpha 0 A with a function of the difference omega A, they rewrite it as a rational function of omega A, and zeta A. This involves expressing Q A as a polynomial in terms of zeta A and omega A, with coefficients QD1, Q1, and Q0. This transformation allows for a more detailed analysis of the relationship between these variables and facilitates further mathematical manipulations. In polynomial manipulation, rewriting functions in a specific form is crucial for further analysis. To achieve this, polynomials Q0, Qd-1 are introduced, which are related to a polynomial p with root alpha. The key transformation involves expressing p in the form zeta minus alpha, p alpha, zeta, where p alpha is a polynomial of degree d-1. This rewritten form enables the bounding of coefficients in terms of omega A, which has significant implications for the function zeta A minus alpha K alpha 0 A. To ensure the validity of this approach, the authors establish conditions for functions V alpha 0 and V alpha star operator, demonstrating their satisfaction for the chosen parameters. The technical underpinnings of this method rely on complex mathematical expressions, highlighting the importance of polynomial bounds and function rewrites for achieving the study's objectives. By carefully controlling the polynomial coefficients and exploiting the properties of the rewritten form, the authors paved the way for further investigation and insight into the underlying mathematical structures. The application of resurgent analysis spans various fields, including physics, mathematics, and control theory. It begins with the connection between resurgent functions and the Borel transform, a key tool in resurgent analysis. The concept of shifted Witten classes and their relation to topological recursion is also discussed, which is fundamental in the study of moduli spaces and intersection theory. The paper explores the relationship between resurgent functions and the Laplace transform, crucial in differential equations and control systems. The discussion on divergent series and their role in resurgent analysis highlights the importance of summability methods and resurgence theory. The authors also emphasize the significance of complex analysis, particularly the work of Olfers and Schief, in understanding resurgent functions and their applications.